You remember Lord Kelvin? Lord Kelvin said that if you, oh man, this is kind of gross food coloring. There we go, let's get a little bit more going on there. Woo, look at that sucker dance. Okay, all right, that's what I'm talking about. Now, Lord Kelvin said that QC over QH was equal to, oh man, now I'm gonna be all green all day. All right, Lord Kelvin said QC over QH was equal to TC over TH. And in fact, he used that to define what temperature means. And as he defined that, some folks noticed that if you get everything with C on one side and everything with H on the other side, you could get this beautiful equation. It says QC over TC is equal to QH over TH. Let's take a moment and talk about what this means. This means the heat leaving the cold reservoir divided by the temperature of the cold reservoir has to equal the heat leaving or entering the, this is the heat entering the cold reservoir. This is the heat leaving the hot reservoir divided by the temperature of the hot reservoir. So these things then are a constant. This must be some constant, and it would apply for any reservoir at any temperature. And we define this then, this interesting constant, let's define it to be entropy. We're going to say that Q divided by T is a change in entropy if there's a reversible process. So entropy is, well, I think the easiest word to associate with entropy is disorder. So if something is disorganized, it has a lot of entropy. If I, for instance, take a deck of cards and it's brand new and it's all stacked ace, 2, 3, 4, 5 like that, and I take it and I spread it all over the floor and then just grab them in whatever order they are, I've increased the entropy of that deck of cards. Because it was previously structured and ordered and beautiful, now it will be chaotic and random. But the reason that entropy increases whenever I do something is because order is unlikely. This is a statistical thing going on. Order, that's a Q? Wow. Order is unlikely. You can tell your mom that when she asks you to clean your room. Order is not likely to occur randomly. So if you want to order your room, you have to expend a whole bunch of energy to do that. I'm getting ahead of myself, but I'd like to move this thing, and I'd like you to notice that if you take this YouTube video and play it backwards, that will look really, really, really weird if this random distribution of green is concentrated back at a single point. That is very strange. So our idea here is that the entropy must have increased. So let's look at this definition of entropy a little bit more, then we have some more room. What I'm saying is, as heat, let me say first, as heat enters a substance, its entropy, which is S, sorry, it's probably German or something, its entropy increases. And we could also say that as heat leaves a substance, its entropy decreases. Because all we need is Q to be negative and we'll have entropy going down. But here's the problem. If you take two things and one of them is cold and the other one is hot, and you set them next to each other, then sure, the temperature, let's give these guys some temperatures. Let's say that this guy is 350 Kelvin and this guy over here, the blue one, is 200 Kelvin. I agree. T cold is 200 Kelvin, T hot is 350 Kelvin. I agree with you that this one will be gaining entropy and that one will be losing entropy, but let's look in detail about what that's going to be. delta S for the hot will be, oh shoot, I guess it's going to be Q, because I don't want to quantify Q, but it's going to be Q hot divided by T hot. And heck, let's just decide some specific heat for it. I don't know, what do you want to give this? 100 joules, that's fine. 100 joules, and that's going to be a negative number because heat is leaving the hot, divided by 350 Kelvin, and then I can calculate delta S for the cold, and that'll be, well, it's going to be Q cold over T cold, and that's 100 joules, because energy must be conserved, divided by 200 Kelvin. So do you see that the increase in energy of the cold reservoir is greater than the decrease in entropy? Did I say energy? Oh my gosh, I should remake this. The decrease in entropy of the cold, sorry, oh my gosh, slow down. All right. I'm saying that this guy has delta S increasing because it's getting heat. And this guy has delta S decreasing. S, rather, is decreasing here. S is increasing there because heat is flowing, well, he will be flowing this direction. Heat flows that direction, so entropy increases for this guy and decreases for that guy. But the increase in entropy over here is greater than the decrease in entropy over there, so the universe as a whole, let me write this down, delta S for the universe, and we are very concerned about the ultimate death of the universe, and this is contributing to it, delta S of the universe is greater than 0. Because this is not a reversible process. But if instead we design an engine and we make this process reversible and we get some work out of it, then we could very slowly play it backwards and everything would be fine. So my point is, if you ever take a hot thing and set it down next to a cold thing, you are increasing the entropy of the universe, and entropy is related to usable energy. I guess entropy decreases usable energy, and you are increasing the ultimate heat death. You're bringing about the ultimate heat death of the universe where no energy is actually useful. Because when entropy is low, like in the early universe, entropy was incredibly low. There was a whole bunch of stuff here and a whole bunch of nothing everywhere else. So as entropy is low, there's an amazing amount of usable energy. But if everything is random and even, then there will be no usable energy, and good luck trying to live in such an environment. So this is the fate of our universe as I see it. We could be a little bit more careful about it. We could say universe entropy. Universe entropy is like this. Universe entropy is like delta S universe equals 0 if reversible processes occur, and delta S universe is greater than 0 if irreversible processes occur. And an irreversible process is one that you can't do the other way, and that is everything that happens, except an ideal engine. Ideal engine is not, it is a reversible process. You can play that sucker backwards and get that energy right back out. And what else? Oh, irreversible processes would be setting a hot thing next to a cold thing because the heat will flow from the hot to the cold. Remember we said that's the arrow of time and all that nonsense? So my argument is you're now ready for the third law of thermodynamics. Are you? Nah. Yeah, let's do it. Third law of thermodynamics, and we'll just end this chapter. Here we go. There is much, much more to know about entropy, but I'm not the guy to teach it, and this isn't the place to learn it. Find somebody who knows more about it. Third law of thermodynamics. There we go. The third law of thermodynamics says you can't get to 0. You can't get to temperature equals 0 Kelvin. It's, this is great. I like to call the third law of dynamics, it's not going to be okay. when somebody tells you everything's going to be okay, they're wrong. So the third law of thermodynamics says you can't get to 0 Kelvin because, now why would that be the case? Because if I had anything at 0 Kelvin, first, in order to say that I need to get to 0 Kelvin, I have to have a bunch of things at 0 Kelvin already. So I've got this thing, and it's got some temperature, and I'm going to say it's not equal to 0 Kelvin. And then I've got these other things, and they're all very cold, and they have the same mass. I've got a lot of them, though, and I've got them all stacked up, and they're all at 0 Kelvin. And so this is at 0 Kelvin, and this is at 0 Kelvin, and this is at 0 Kelvin, and this is at 0 Kelvin. So you understand that my only plan to get to 0 Kelvin is to already have an infinite number of things at 0 Kelvin. And I'm going to take these suckers one at a time, and I'm going to set them next to this guy. And I'm going to be like, okay, now it's going to be at temperature, what? I mean, I guess it'll be half its original temperature. It's going to be a little bit different temperature. It's going to be temperature equals, we can call this T naught, this original one. T naught, and that's where it started. And then I'm going to say T final is 1/2 T naught because it has been cooled off by one of those suckers. And then I could take, now I could take another one of these. This one is used up because it's also at T final. So I'm going to throw that away. I'm going to take this one and bring it in here. Maybe I brought that one over there. And then I put it here. And it's going to cool off even more. And then I'm going to say T final is, well, T final in this case will be 1/4 the original temperature, right? Because I'm cooling it off more. And you see that ultimately I can keep splitting its temperature in half, but can you ever get to 0 by dividing by 2? Well, you'd need an infinite number of those, and you need an infinite amount of time. So, oh my goodness, in order to get any single thing to 0 Kelvin, we'll need an infinite number of things already at 0 Kelvin, which is rather ridiculous. And that's why we don't think that anything can get to 0 Kelvin. So, here's the issue. In your life, you're increasing the entropy of the universe. However, your life has value. Also, you can decrease the entropy of certain systems, like you can clean your room when your mom asks. And that's cool. You do actually decrease the entropy of your room. But as you're decreasing the entropy of your room, what I mean is entropy is disorder, so you're decreasing the disorder of your room. As you order your room, you are vastly increasing the disorder of your cells, for instance, which are using energy to do that work. And it's harder to think about it in that way, but oh my goodness, study entropy. It's absolutely fascinating. Goodbye. Of the hot reservoir. So these things then are a constant. This must be some constant, and they would apply for any reservoir at any temperature. And we define this then, this interesting constant, let's define it to be entropy. Kelvin said that QC over QH was equal to, oh man, now I'm going to be all green all day. All right. Lord Kelvin said QC over QH was equal to TC over TH. And if you remember Lord Kelvin? Lord Kelvin said that if you, oh man, this is kind of gross food coloring. There we go. Let's get a little bit more going on there. Woo, look at that sucker dance. Okay. All right. That's what I'm talking about. Now, Lord Kelvin, in fact, he used that to define what temperature means. And as he defined that, some folks noticed that if you get everything with C on one side and everything with H on the other side, you could get this beautiful equation. It says QC over TC is equal to QH over TH. Let's take a moment and talk about what this means. This means the heat leaving the cold reservoir divided by the temperature of the cold reservoir has to equal the heat leaving or entering the, this is the heat entering the cold reservoir. This is the heat leaving the hot reservoir divided by the temperature of